Alright, in today's discussion, we're going to talk about Newton's method. Now, this is a method that Newton developed to estimate the x-intercepts of a function. We're going to start by saying, in Newton's method, for approximating zeros of a function, and zeros are just another word for the x-intercepts, we can let f of c equals 0, where f is differentiable on an open interval containing c. Then we can also say, to approximate c, we can use the following steps. And I'll show you how we get some of this as well. So the first thing we're going to do is we're going to make an initial estimate. We're going to call that x1, x sub 1. That initial estimate, we're going to say it closes, or not it closes, it is close to c. So it might be helpful to check a graph, just so you can get an estimate as to where you think your first estimate might be. Once you've made that estimate, you are going to then, in step 2, determine a new approximation. We can use the following recursive formula, and I'll show you how we derive this formula in a minute. The new approximation, we can say x sub n plus 1, so it's our next approximation, is equal to the previous xn, so the previous approximation we had, minus f at xn over the derivative, the first derivative at xn. We can also say, or once we've done that, we can move on to the third step, when the absolute value of our xn absolute value of x sub n minus x sub n minus 1. So our previous approximation, or our current one, minus our next one, is within a desired accuracy. Then we can let our x sub n plus 1 serve as the final approximation. Otherwise, we return to step 2 and calculate a new approximation. And we repeat that step until we get an approximation that either is not changing or it's within our desired accuracy. What we can say is that each successive application of this procedure is called an iteration. So I said I was going to show you how we get the formula for step 2. I'm going to do that. So there's a couple things we need to just keep note of. We're going to look at the point-slope form of an equation. I'll just abbreviate that as PS form. As a reminder, that's y minus y1 equals m times x minus x1. But we're going to replace a couple of these values with some other stuff we know. Now, we're going to start by saying our first estimate we're going to let x equal x1. So then what we can do, if we allow a point to be x1 f of x1, where the f of x1 is a y value, we can plug that into our point-slope form. We can have y minus f of x1 equals, now also keep in mind that the derivative looks at the slope at any given point. So we can say m is the first derivative at x1. So y minus f of x1 is equal to f prime of x1 times x minus x1. And since we're trying to find a x-intercept, that means we need to let y equal 0. So that means we can write 0 minus f of x1 equals f prime of x1 times x minus x1. Now, we want to solve this for x, so we're going to do a couple things. One, we can just ditch our 0. Next, to solve this, we're going to divide first by our derivative. So we're going to say that negative f of x1 divided by f prime of x1, that's equal to x minus x1. And we're getting there. We're solving this for x, so we're going to now add x1 to both sides. So that means x is going to equal x1 minus f of x1 over f prime of x1. So this would give us our first estimation for our x-intercept. We can repeat the process by now replacing, in fact, our new approximation would make this x2. To continue the process, what we do is we can go through everything again, but we're going to replace all the x1s with x2s. So what we'll see when we do all of that is we're going to get x3 is equal to x2 minus f of x2 over the derivative, first derivative at x2. If we were to generalize this, then we get that formula we looked at on the previous slide. The xn plus 1 equals xn minus f of xn over the first derivative at xn. So Newton's method is nice because we can repeat this process to approximate a y value, or not a y value, an x value where the function crosses our x-axis. So if we're diving into our first example, we're going to use Newton's method to approximate a0, a possible x-intercept of the function f of x equals x squared minus 2, and we're going to use x, our first estimate, to be 1. That's our initial guess. So there's a few things we need to first know. We do need to find the derivative. So if we were to take the derivative of this function, we're going to get 2x. So we can now set up our formula, which was, or we can write it as x n plus 1 equals xn minus, we know f of x, but we're going to find f of xn. So we're going to replace x squared with xn. So we're going to have xn squared minus 2 over, and again, we're going to do the same thing in the derivative. Replace x with xn. So we're going to have 2xn. Now, if we want to find x2, that means we're looking for x of 1 plus 1. So we're going to take x1 minus x1 squared minus 2 over 2x1. And we know x1 is 1. So this is going to be 1 minus 1 squared minus 2 over 2 times 1. Well, we know 1 squared is 1, and 1 minus 2, that is negative 1. And 2 times 1 is 2. So if we have 1 and we subtract negative 1/2, that's the same as 1 plus a half, which is going to be 1.5. So that means x2 is 1.5. We're going to repeat this process until we see if something seems to just about start repeating. So that means now we're going to find x3. In fact, with this specific example, and I didn't write this down, we're going to do 3 iterations. So we've done 1. In fact, we just did the first. We're going to do 3 more. So we are, or complete a third. We're going to now take x2 and plug it into our formula. So we've got 1.5 minus 1.5 squared minus 2 over 2 times 1.5. Now I would just go and put this into my calculator. And putting it in my calculator, I'm going to get about 1.416667. So the 6's repeat. That's fine. Now I'm going to take that value and I'm going to try to find x4. We're going to do another iteration. So we're going to go 1.416667 minus 1.416667 squared minus 2 over 2 times 1.416667. Again, I would just plug that into my calculator. From my calculator, get that to be about 1.414216. So that means my third iteration, we've done this 3 times. We had our initial guess, our first iteration, second, third. We can approximate that the 0 of x squared minus 2 is at about 1.414216. Which, if we were to actually solve this using square roots, the square root of 2, while not exactly 1.414216, it's pretty close. So let's look at another example. And I've only got a couple we need to look at in this lesson. So example 2, we are going to use Newton's method to approximate the zeros of f of x equals 2x cubed plus x squared minus x plus 1, and we are going to continue this. Part of what we're looking at here is continuing the iterations until two consecutive or successive approximations differ by less than 0.0001. So, what we're going to do, what I would recommend doing, is using your graphing calculator just to see where you think this might cross. Now, I'm not going to pull up a graphing calculator, but I do know from my own calculator that I have next to me that I see that the 0, it happens between -1 and -2, and that's the only 0. In fact, the 0 is closer to -1, so we could say that our approximation is about, our first initial guess is maybe -1.2, and we'll continue redoing iterations until we get within our approximation constraints of that 1/10,000th. So we're going to find x2. That means we're going to take x1, -1.2. We're going to subtract f of that, f of -1.2, over f prime of -1.2. So we do need to figure out f prime. If we know f, that's not too hard. We've been finding derivatives for a while now. Our derivative is going to be 6x squared plus 2x minus 1. I'm going to just use my calculator to figure out what is f of -1.2 over f prime of -1.2, and then subtract that from -1.2. So I'm going to do that. When I do that, I'm going to find that that's going to give me about -1.23511. So now I'm going to utilize that to find x3, my second iteration. So we're going to have -1.23511 minus f of -1.23511 over f prime of -1.23511. And again, I'm going to just use my calculator to do this. When I do that, I'm going to get that my second iteration, my x3, is going to be -1.23375. Now, since I am looking to round to the nearest 10,000th, I would at least be taking these numbers I'm calculating and go to the 100,000th. So let's check our next iteration, because these aren't within a 10,000th. So we're going to look for x4, or we're going to take -1.23375, and we're going to subtract f of that value. I'm just going to put x3 here over f prime of x3. I plug those into my calculator, and I get -1.23375 again. So that means I have the number I want. In fact, two successive approximations in a row that give me the same number means they're within my required range of that 1/10,000th. So we can say our estimated 0 of this function is -1.23375. I am going to show you as well a method, or not a method, an example where this Newton's method does not work. That'll be in our next video.